Today we will say about frequency shift keying. Frequency shift keying is a digital modulation technique that allows data transmission by changing the frequency of carrier wave according to the digital modulating signal. So here the carrier wave is changed with respect to the input digital signal. So in the figure, if you see the first figure, it represents the digital signal, input signal. Second waveform shows the high frequency carrier waveform, and third figure represents the low frequency carrier waveform. Fourth figure represents the FSK modulated wave. So here you will be having the combination of high frequency as well as low frequency waveform. So in this case, when you are having a digital data as 1, you will be getting a high frequency carrier signal as a output, and when you are getting a digital signal 0, you will be having a low frequency carrier waveform as the modulated wave. So likewise the FSK modulated waveform will have high frequency as well as low frequency waveforms. So the high frequency waveform represents 1 and low frequency waveform represents the data 0. The simplest form of the FSK is binary frequency shift keying. Here you are having two carrier frequency signals. One is high frequency carrier signal and another one is low frequency carrier signal. The frequency of the carrier wave is changed between the binary signals, binary values of the modulating signal. So thus the frequency of the carrier shows variations according to the binary message signal. The frequency of the carrier waveform will show the variation depending upon the message signal. So in this case, it is showing the high frequency signal when the digital data is 1, and similarly it gives low frequency signal in the case of low level data, that is for message signal 0. Since you are having two frequencies, you will be having two oscillators to generate high frequency signal as well as low frequency signal. So here you are having oscillator 1 which generates the high frequency carrier signal whose frequency is f1, and oscillator 2 it generates a carrier signal whose frequency is f2, it is having a low frequency. So both are given to a switch, and on the other end a binary input is also given, so that you will be getting a modulated waveform as an output, which will be a frequency shift key. So from the block diagram, it is clearly given that you are having a binary signal given to that switch, as well as you are having two carrier frequencies, and in that you are having two switches. So in the case the binary signal is 1, the switch 1 will be closed so that the high frequency signal will be given as the output, and in the case the input to the binary signal is 0, the low frequency signal should be given to the output, so that the switch 2 will be closed and the oscillator 2 will be giving the low frequency signal. So hence it is clear that low frequency signal is achieved in case of low data bit of the modulating signal. However, in order to eliminate phase discontinuities of the signal at the output, an internal clock is provided at the oscillator. Thus the high or low frequency signal is selected according to the digital modulating signal. Thus an FSK modulated wave is transmitted and achieved at the output. So after transmitting, you will be going for the detection. So detection of FSK signal has similarly two processes as seen in the ASK: coherent detection and non-coherent detection. Coherent detection needs synchronization between the transmitter and receiver. In non-coherent, you don't need to have any synchronization. You will be having an envelope detector. So here the FSK signal will be given to the product modulator. You will be having two product modulator, two integrator, which is combinedly called as correlator 1 and correlator 2. And once again the output of the integrator is given to the decision device. Then the binary data is taken out. In coherent detection, you will be giving the FSK waveform to the product modulator. You will be having a product modulator, two product modulator, So one FSK waveform will be given to the two product modulator, and for each and every product modulator you will be having a carrier wave. So two carrier waves, one will be high frequency carrier wave and another one will be a low frequency carrier wave. So this will be multiplied in this product multiplier and it will be given to an integrator. So the integrator will combine these two signals and it will be given to the decision making device. So in the case if the signal strength is very high, in the case of integrator 1, integrator 2 signal strength will be very low. So in the decision making device, if the signal strength 1 of the integrator is high, means it gives the decision as binary data 1, because it is a high frequency waveform coming from that correlator 1. In the case of integrator 2, if it is having the signal strength high when compared to integrator 1, so it is having a low frequency carrier waveform. Therefore, the decision making device will give an output as 0, since the integrator 2 is having the signal strength higher than the integrator 1. So the output will be 0. So in the case of non-coherent detection, you will not have the carrier waveforms here. So both the frequency shift keying waveform is given to the band pass filter, two band pass filters and two envelope detector and a comparator. So here the comparator is nothing but the decision device, so that the binary signal is once again achieved here. In non-coherent detection, no need for any synchronized carrier required at the detector. So it consists of two separate bandpass filter that is tuned to two different frequencies. The output of this bandpass filter is then fed to the envelope detector, which generates two separate output according to the signal achieved from the bandpass filter. This decision making device compares the output of the two envelope detector. When the output of the detector 1 exceeds detector 2, then the logic is 1. When the output of the detector 1 is exceeded by detector 2, then the logic is 0. So this will be the output. The output will be 1 only when the detector 1 exceeds detector 2, and output will be 0 when detector 1 exceeds the detector 2. Thus the original bit stream is generated by the detector. We will see the advantages of frequency shift keying. FSK provides better noise immunity. The signal transmission through FSK is quite simple. It is suitable for long distance data transmission. Bit error rate performance is better than ASK. The disadvantages of frequency shift keyings are it utilizes more bandwidth as compared to ASK and PSK. Thus, is not bandwidth efficient. So here bandwidth is not efficient when compared to ASK and PSK. Detection of the signal at the receiver is somewhat complex. So in the receiver side, detection is somewhat complex. Applications, if you see, the technique is used in high frequency data transmission, extensively used in low speed modems. Thank you.